So this is the outline for chapter 23. So we will introduce electric bus and then talk about the Gauss law, which is the main part. And then using the Gauss law, we will try to derive some of the electric field generated by different topology. Yeah, using different type of symmetric property. Okay, so this is the overview of the electromagnetism. So in physics 2, you mainly learn the electromagnetism, at least up to chapter 33. And of course, in chapter 32, we will talk about the Maxwell equation. And just as I described in the first lecture, I've already mentioned that if you really need to use two words to describe electromagnetism, which should be Maxwell equation, and we will learn it one by one. So in this chapter, we will learn about the Gauss law. We'll learn the Gauss law. In chapter 29, we will learn Ampere's law. In chapter 30, we will learn the Faraday's law. And of course, in 32, we will also learn this one is the magnetic version of the Gauss law. So it is mostly the same, except the right-hand side will be a zero for the magnetic version. So it is nothing special. And of course, in chapter 32, I will also introduce the differential form, or here it mentioned the point form, but yeah, that the notation here is a bit different from the textbook, but I just use it here to let you know. We have the overview of this one, so I will try to let you know at any time where you are actually at. So now we will try to learn the Gauss law, and we'll learn it one by one. Okay, so now let's try to introduce a concept called the electric bus. Electric bus. So flux in Chinese is 通量. So as much as we know in previous chapter, we have the concept of the electric field line. So it specifies the direction and visualize the magnitude. Yeah, the relative magnitude. You can't really know the exact magnitude, but from the electric field line, but at least you can know which part is of the electric field is relatively large or which part is relatively small. And now we introduce another concept called the electric flux. Here it says Gauss law related to the electric field at points on a closed, or we usually call it the Gaussian surface, to the net charge enclosed by that surface. So here it has a very important concept called the Gaussian surface, which means a closed surface. 封闭曲面 closed surface, or in this textbook, it usually call it a Gaussian surface to the net charge. So of course, this figure is in 2D, so you can imagine it should be a sphere rather than a circle. But it is good enough for demonstration. So now we consider this circle. Here we have a charge. And then it generates the E field with 8 arrows pointing outwards. And here it specifies the charge Q, the charge plus Q. So the E field pointing outward. And here we have another charge, although it is somehow like smaller, but actually it is 2Q. This is 2Q. Okay, so it generates 16 arrows pointing outside. And for this one, this is negative 0.5 Q. So it has 4 arrows pointing inside, because this is negative. So the E field is pointing inside, but here we have 4 arrows. Here we have 16 arrows. And here we have 8 arrows. Okay. So this means that when we try to count how many arrows are going through this surface with the dotted orange line. So we have 8 arrows going through it. We have 16 arrow going through it. We have 4 arrows going through it. But of course it is inside, so it means that this is a negative charge. So in the space, we can actually define any closed surface or any Gaussian surface, and we try to count how many arrows going through it. And each will certainly means that how many charge are inside this area, because as much as we know, there are 8 arrows going out, then there should be a positive charge Q here, and we have 16 arrows here, so this charge is positive, and it is a 2Q, and we have 4 arrows going inside, so it should be negative 0.5 Q here. So this is the simple concept about the electric flux. We try to count the electric field over a closed area, or it is not necessarily a closed area, but at this case, we consider the closed area. It will give us some interesting property. So here, let's try to define it in a more rigorous way. So here we define the area vector, just like the distance vector. So you may be hard to imagine why an area can be a vector, but yeah, it's just a definition. So here, suppose area vector dA for an area element. On a surface is a vector that is perpendicular. So because when we try to define a vector, we should define both of the magnitude and also the direction. So the direction of this vector is actually perpendicular to this element. Suppose it is small enough, even though it is a curvature, we can actually cut it into a very, very small area, and then we can regard it as a plane, a part of a plane. So we can also define the direction perpendicular to this plane, to this element. And of course, you may ask, actually, perpendicular to this plane actually means 2 direction. Maybe, yeah, this one is perpendicular to the plane. This one also perpendicular to the plane. So there may be two possible direction for this vector. Yes, that's correct. And if it is not a closed surface, then yeah, which direction you choose is just up to you. But for closed surface, we will have some rules to determine the direction of this area vector, and we will talk about it a bit later. So we know the direction of the area vector should be perpendicular to this element, and the magnitude should be the same as the area, because this is an area vector. So area should be the magnitude of this area vector. And now we can try to define the electric flux. So the electric flux, we call it d phi through a patch element, which with area vector dA is given by a dot product. So this is the d phi is the electric flux. is defined is defined by E dot dA. E dot dA. E is the electric field, and then dA is the area vector, and then we use the dot product. Dot product means we have the magnitude of E here. We have the magnitude of dA, which is the area, Maybe we can just write this one as dA. E times dA. So this is the magnitude of E vector. This is the magnitude of the area vector. And then we need to multiply it by cosine of theta. Theta is the angle between E and dA. So we need to multiply by cosine theta. I suppose you should have learned it in high school physics or high school mathematics. So this is the inner product, how it is operate. Okay, so yeah. Yeah, maybe I can just mention some of the inner product for the unit vector. Inner product for unit vector in Cartesian coordinate. So we have I, which is the unit vector of in x-axis. J is the unit vector of y-axis, and k is the unit vector in z-axis. So if we have I dot I, which is 1, j dot j, which is 1, k dot k, which is 1. And if we have I dot j or j dot I, which is 0. And then I dot k and k dot I is also 0. And then we have a j dot k, 0, 0, k dot j, which is also 0. So actually, dot product, we need 2 operands. So, and we have 3 choices for both. So we have totally 9 combination here. So if 2 unit vector are the same, then the dot product will be 1. If they are not the same, then the dot product will be 0. Because if 2 vectors have the dot product to be 0, which means they are perpendicular to each other, and the other way around. Yeah. Oh, sorry. Okay. So yeah, we simply mentioned the dot product for the unit vector in Cartesian coordinate. So now, yeah. So now it talks about that. Yeah, there are 3 cases. So the first one, A, is like sorry, just raise it here. So an electric field, it says an electric field vector pierces a small square patch on a flat surface. So we have a E field pointing this side, and then of course dA is perpendicular to the element. So yeah, so we can calculate d phi like this. And if yeah, so it is somehow like it only consider the EX component. It will ignore the EY component because actually EX is actually E cosine theta. So if you just merge them together, it is like E cosine theta and then times dA. So it only consider the x-axis component because the area vector is in the direction of the x-axis. So yeah, so we only consider EX, yeah, in that case only. Yeah. And yeah, EX here. So it is like d phi equals EX dot EX times dA. Okay, so yeah, so only the x-axis component actually pierce the patch, the y component skim across it, 就是擦过。Okay, so the area vector of the patch is perpendicular to the patch. Okay, so now we can also define. Yeah, we as much as we have the define, so we can just integrate it. So it is something like the integration of a d phi over a surface, or yeah, or whatever. So the whole flux is the integration of the small electric flux integration together. So in that case, and as much as we know, d phi is E dot dA, dA. So we have a phi equals to this integration, which will be something like this, something like this. Okay, and of course the SI unit is important. The SI unit is N M square over C, because the SI unit for E is N over C. SI unit for area M square, meter square. So they multiply together. So N M square over C, like this. Okay. So here it defines two things. One thing is the total flux. Total flux. Total flux through a surface. It doesn't necessary to be a closed surface. So surface, only a surface is enough to define the total flux. So maybe you can just have a surface like this, or maybe just a perfect rectangle, plane that you can define. Yeah, maybe this one is S1. We call it S1. So this one is S1 integration of E dot dA, and it will be the flux. Suppose we have some E field going through this surface. Then we define the total flux by this surface integration. And yeah, and the second definition is the net flux. To define the net flux, we need a closed surface. We need a closed surface, which is used in the Gauss law, or usually in the textbook it is called Gaussian surface. As just I mentioned, Gaussian surface. So it's given by this one. So the only difference between the total flux and the net flux is this circle. And of course, this circle means a closed surface integral. So the only difference between this definition and this definition. Yeah. So this is total flux. This is net flux. Okay. So just now I mentioned that the direction of the area vector can be two cases, either perpendicular to one side or the opposite side. But for the closed surface, we will define it like it is pointing out of the volume, which means that suppose we have a Gaussian surface, which is a closed surface here. So you can actually tell what is inside this surface, what is outside this surface. So as much as we have, for example, if we have this area, and of course you need to say, the vector is perpendicular to it. So this is dA. Or before we talk about inside or outside, then maybe you can say, inside is also okay. But remember, in calculus or physics, we always define the area vector pointing outside. So we always use it pointing outside from this closed surface bounded region. Okay. So in that case, if uh, if the phi is larger than 0, which means that the flux is going outward. If phi is smaller than 0, which means that the flux is going inward. It's going inward because now we already defined dA is pointing outside, and as much as you know, E dot dA is something like E times dA cosine of theta. So E and dA are the magnitude of the vector, so they must be larger or equal to 0. Yeah. And yeah, for the cosine theta, if theta is between 0 and 90 degree or 0 or pi over 2 radian, then cosine of theta should be a positive value. So cosine of theta is positive if theta is between 0 or pi over 2, 0 to pi over 2. And it should be negative if theta is between minus pi over 2 to to 0, or pi over 2 to pi, something like that, or pi over 2 to pi, depends on how you define the angle. Okay, so yeah, pi over 2 to pi is good. Yeah. So if this theta is an acute angle, then this dot product will be a positive value like this one. And if they're perpendicular to each other, then cosine theta is 0. So E dot dA will be 0. And if this is larger than 90 degree, larger than pi over 2, then this dot product will be smaller than 0. And of course, if you define a Gaussian surface, you try to calculate the E dot dA and try to integrate them together. It doesn't necessarily mean that for the whole surface, all the points will have positive value or all the points have negative value. Maybe some of it has positive, some of it has negative value. Then after summation, then part of them will cancel out each other. So here we only consider after the summation, if it is positive value, which means that overall, maybe something going in, you can just imagine there is a classroom, then there are some students there, and some students may go inside the classroom, some students may go outside the classroom, but finally we will try to count how many numbers in the classroom for every hour. Then you can see there is a net flow of students going in or going out of the classroom. We don't necessarily count every individual student. We just count the trend or the flux or the flow of the overall student number. So this is something similar concept here. So we talk about the flux, whether it is going in or going out. So for calculus class or physics class, we always define outward to be positive, inward to be negative. Yeah, it is something like if you have a surface, and then this is dA, and yeah, if it is going outward, okay, so this is positive, and yeah, so for this point dA, something like that. Yeah, something like that. And still for this case, dA pointing outward. And if the E field are generally pointing inward, generally pointing inward, then you can see E dot dA will be negative number, So here we don't really talk about much about the how really the calculation is done. We only talk about only this positive or negative value only. So maybe let's stop here today, and we will continue next week. Okay.